Hey everybody, welcome back. Today we are taking a look at acids and bases lesson 3. This lesson is going to combine concepts from yesterday's lesson and the solutions unit. Before we get started, we're going to do some review questions. I'm going to walk through the first row of this table with you and then give you a chance to try it on your own. So we have been given hydroxide concentration. From here, we're going to find POH, hydronium, and pH. Now, you may not find them in that exact order depending on how we work the flow chart. So let's go down here and create our flow chart. When I'm creating the flow chart, I like to use the relative location of each value that we have. So if hydroxide, we know is going to be in this corner right here, which is 9.80 times 10 to the negative 4 moles per liter. From here, we can only go one way and find POH. The way that we do that is go negative log of our hydroxide concentration, 9.8 times 10 to the negative 4. So let's plug that in, negative log 9.80. This E represents times 10 to the power of negative 4. Close your bracket, enter, and we get our POH. Now on paper, I can show a rounded answer, but on my calculator, I'm going to leave it all there so that we can use it for the next step. So go up. Our POH is 3.009. Now, again, a lot of you are going to ask me, well, why does this have 4 significant digits? Well, it doesn't. When you're looking at POH and pH values, only these digits here on the right side of the decimal apply. So yes, we use regular rounding significant figure rules for hydronium concentration and hydroxide concentration, but for POH, only these digits matter. I'm going to go ahead and now add this value to our table. From POH, we can find pH. To find pH, we're going to go 14 minus our POH, which is 3.009. Now I'm doing the rounded value here just to save paper space, but in my calculator, I'm actually going to go 14 minus my answer. Okay, and I get a pH value of 10.991. Again, those are 3 significant digits because it's a pH value. So 10.991. From here, we can then calculate our hydronium concentration by going 10 to the power of negative 10.991. Again, I'm showing a rounded value on my paper, but in my calculator, I'm going to go 10 to the power of negative of my answer. So when you are doing the answer value, do know that it's taking the last thing that you calculated. So if it's not the last thing, you will have to scroll up and select. There is my hydronium concentration. So hydronium, I get a value of 1.02 times 10 to the negative 11 moles per liter. And remember, your pH and your POH are unitless. Awesome. You can go ahead and try the next row on your own. If you feel comfortable, pause it, go ahead and you can check your work at the end. If you would like me to walk through with you, you can follow along with me now. Okay, so here what they've done is they've given us a pH value. Okay, so I'm going to start off with the relative location of pH, which is here on my table. What do we want to find first? How about we find hydronium concentration first? So let's go this way. My pH is 5.254. To find hydronium concentration, I need to go 10 to the power of negative 5, oh boy, let's try that again. Negative 5.254. Let's plug that in. 10 to the power of negative 5.254. Okay, I get a hydronium concentration of 5.57. I get 3 significant digits because I have 3 significant digits in my pH. Moles per liter. Great. Now, what else can we find? We can't really go further from hydronium, so I go back to my pH. Oh, hey, we can also find POH if we have our pH value. 14 minus 5.254. So I'm going to go ahead and go 14 minus 5.254. And I get a POH value of 8.746. Okay, from here, we can then find our hydroxide concentration. The way we do that is we go 10 to the power of negative 8.746. So I'll show you another way to select this on your calculator. 10 to the power of negative, then we can go ahead and scroll up and click enter, and that'll put that number there. Click enter, there is our hydroxide concentration, 1.79 times 10 to the negative 9 moles per liter. Great. Complete the following statements using the words increase or decrease. Diluting an acid would blank hydronium concentration. So if you are diluting an acid, you are decreasing the hydronium concentration. Okay, so you are decrease hydronium concentration. If hydronium concentration is decreasing, that means your pH is approaching the basic side, or it's approaching neutral, which means that it is going to increase the pH. Let's draw a little bit of a diagram to kind of visualize what I'm saying here. Here's our pH scale, 1, 14, 7. Okay, so our hydronium concentration increases. So hydronium concentration increases this way. This way, our pH decreases. Okay, let's do red to represent the other direction. So this way, okay, let's do that again. So this way, as we become more acidic, the reason we become more acidic is because our hydronium concentration increases. Therefore, we have a lower value in pH. Decreases. Okay, if we are going this way, our hydronium concentration is decreasing. And we can see that our pH is increasing. Okay, so let's complete the last statement. As pH decreases, hydronium concentration increases. All right. Okay, last review question here. A solution with a pH of 3 is diluted to have a pH of 5. Does acidity increase or decrease? Well, if we're diluting something, that means it's becoming less. Well, if we're diluting an acid, that means it's becoming less acidic. So in this situation, it's decreasing. By what factor does it decrease? Okay, so let's do some diagram drawing here. 3, 4, 5. From here to here, it's a jump of 10. From here to here, it's a jump of 10. So from 3 to 5, it's a jump of 100. So we are decreasing by a factor of 100. Today's learning goals are to understand how dissolving compounds in water can determine the acidity or basicity of a solution, determine hydronium pH, hydroxide, and pOH from a dissolved compound, and understand how dilution affects pH and hydronium concentration. We will be doing this lesson in 2 parts. I'm going to go over the first 2 today, and we will go over the last learning goal in part 2 tomorrow. Okay, word problems. I remember I used to hate word problems in math. But in chemistry, I feel like they're okay. They somewhat make sense. Example 1. What is the pH of a solution in which 1.2 grams of HCl gas was dissolved in 890 milliliters of water? The first thing I always want you to do in a word problem is write an appropriate reaction. So what happens when acid is placed or dissolved into water is it ionizes. Okay, so this is connecting us back to the first unit. So step 1 is a balanced reaction. RXN stands for reaction. Okay, so I'm going to grab this HCl gas. When dissolved in water, ionizes to form H plus and chloride ions. Remember, ions are aqueous when in water. Step 2 is to set up what we know and what we are looking for. So let's go ahead. We know that we have 1.2 grams of HCl dissolved in 890 milliliters of water. So I'm going to go ahead and list those values underneath. 1.2 grams of HCl. We are trying to determine pH. We're looking for pH of the solution. So now you're going to ask yourself, which one of these 2 values, or which one of these 2 ions will connect us to the flow chart? Is it H plus or Cl minus? Well, remember how I said that if you have H plus, that is the same thing as having hydronium. Well, the reason being is if you form H plus in water, it's going to react with the water. If it reacts with the water, it's going to form hydronium. Okay, so that's why we can have this rule. Okay, so going back, the person of interest now becomes to find the concentration of this. So this is our unknown. We are looking for concentration, molar concentration of H plus. Great. Whenever you're relating concentration, this is a great place to list your volume. So I'm going to go 0.890 liters. The reason being liters is because we always work with molar concentration in moles per liter. Now that we have everything listed, step 2 is going to be find our concentration of H plus. So the way that we're going to do that is write a stoic statement. So we start with what we know. 1.2 grams of HCl times by. Now, from now on, I always want you to convert into moles before you put it in, before you use your molar ratio. So I need to change this gram into moles. So the only way we can do that is use a converter, which is our molar mass. Our molar mass of HCl is 3646. So we can actually list that under HCl, 36.46 grams per mole. So I'm going to divide by 36.46 grams over moles. Great. From here, we now have grams of our known. Grams and grams cancel out, so we have moles of our known. This is the perfect time to use your molar ratio. In front of HCl, I have 1 mole. Remember, ones are invisible in chemistry. Okay, so 1 mole of HCl. Okay, mole cancels out, HCl cancels out, HCl cancels out. What are we looking for? Moles of H plus. Great. But we need to get to our final destination of having units, moles per liter. So I'm now going to go ahead and divide by my volume, 0.890 liters. Okay, so I currently have moles per liter of H plus. Perfect, that is what we are looking for. Okay, so let's go ahead and plug this into our calculator. 1.2 divided by 36.46 divided by 1 multiplied by 1. You don't have to add these in if you know that it'll give you the same answer. Divided by 0.890. And we get a molar concentration of H plus H plus, which we know is equal to our hydronium concentration, which is equal to 0.0369 moles per liter. Great. Now that we have this concentration, we use our flow chart to find pH. So I am going to, okay, so now that we have something that relates to our flow chart, we can use our flow chart to determine the pH of the solution. So step 3 is use the flow chart. I'm going to start off with my hydronium concentration. If I have my hydronium concentration, I can work it this way towards pH. The way that I accomplish this is by going negative log of my hydronium concentration. This right here is my hydronium concentration. So it's 0.36, or sorry, 0.0369 . I'm going to plug that in, 0.0369 moles per liter. Again, I am just showing a couple significant digits on my paper, but when I am doing it in my calculator, I am going negative log, select that answer or click answer, it'll enter, close the bracket, Oh, let's not put that there. Enter, and I get a pH of 1.43. 1.43. Now, I cannot stress enough, if you mid-round, it is going to affect your answer quite a bit. So make sure you are selecting your full previous answer and inputting it into your calculator. I am going to round my answer to two significant digits because this guy has two significant digits. So I need two decimal places right there. So my final answer is pH is equal to 1.43. Because this is a word problem, it is recommended that you write your answer in words. So the pH of the solution is 1.43. Okay, there is my final answer. I apologize for this one being a little squished. Okay, let's move on to example 2. What is the pOH of a solution in which 14.20 grams of phosphoric acid is dissolved in 1.5 liters of water? Okay, we are given a mass and we are looking for pOH of an acid that is dissolved in 1.50 liters of water. First step always is you're going to write an appropriate reaction, an appropriate balanced reaction. So acid, when put into water, is going to ionize. So step 1, balanced reaction. Always balanced reaction. So H3PO4, when in water, is going to turn into 3H plus aqueous plus PO4 3 minus aqueous. From here, let's list things that we know and things that are going to connect us to the flow chart, because we need to get to the flow chart to find pOH. We cannot find it from this balanced reaction. So 14.20 grams of phosphoric acid. Now, again, you're going to ask yourself, between the two ions, which one's going to connect me to the flow chart? And it's usually going to be H plus or hydroxide. You're looking for one of those two. So this guy is going to connect me to the flow chart. So we need to find molar concentration of this guy. Okay, 1.5 liters. I'm just going to list the volume with molar concentration, because those two usually go hand in hand. Now, from there, you're going to find your H plus concentration, because it will help us find, because it is equal to the hydronium concentration. And because it's equal to our hydronium concentration, we will be able to connect it to our flow chart. Okay, so let's go ahead and start our statement. 14.20 grams of phosphoric acid. We need to convert this into moles before we can use our molar ratio. And the way that we do that is by using our molar mass. Our molar mass of this guy, the molar mass of this guy, I'm going to list it right underneath, is 98 grams per mole. So I'm going to go ahead and sub that value in. 98 grams per mole. Grams cancels out with grams, and I am left with moles. From here, now that I have moles of my known, I can then use that to, I can use my molar ratio to convert this into moles of my unknown. So you're going to go moles. I have 1 mole of H3PO4, my phosphoric acid, and I have 3 moles of my H+. Let's do some canceling. Moles cancels out with moles. H3 plus, or sorry, phosphoric acid cancels out with phosphoric acid, and now I have moles of my H+. Great. From here, we need to convert this moles into moles per liter, and the way that we do that is dividing by our volume, which is conveniently already in liters. So divide by 1.5 liters, and now what I am left with is moles per liter of H+. Perfect, that's exactly what we're looking for. So we can go ahead and plug that in. 14.0, not 02, 0.20, I make that mistake sometimes, divided by 98 times by 3 divided by 1 divided by 1.50, enter. And I get a molar concentration of 0.2897 ... moles per liter. All right, from here, we're going to use the flow chart, the acid-base flow chart. And in this case, we are looking for pOH. So use flow chart to find pOH. So remember, if we have H+, we have hydronium. They are the same thing. It's a 1-to-1 ratio. So we're going to start off with our hydronium concentration. So H3O+, this is 0.2897 ... To convert this into pH, we are going to take the negative log of this answer. So negative log of 0.2897. Again, on paper, I am showing this, but I'm behind the scenes on my calculator. I'm going negative log. You can either go up and select, close the bracket, enter. I get a pH of 0.537, but that's not what we're looking for. Okay, we are looking for pOH. So I'm going to need to convert this one more time. I'm going to go 14 minus my pH, 0.537. And once that is subtracted out, so we know 14 minus, here we'll do answer this time, enter. My final pOH is equal to 13.462. Let's scroll up to see our significant digits. The least amount of significant digits I see is 3. That was used in the problem, so I do need to round to 3 decimal points in this guy. So here is our final answer. Last example for today. What is the mass of aluminum hydroxide? What is the mass of aluminum hydroxide dissolved in 350 milliliters of water if the pOH is 9.89? So for this one, we're working backwards. Okay, this is an example where we're working backwards, and I will actually go through this in part 2.